Welcome back. In the previous video, we talked about a special characteristic or properties of binary trees. And because of the way binary trees are structured, there's a certain way for us to calculate the number of nodes that they have. For example, on level 0 of a binary tree, that is the very top level where we only have one root node, we can calculate how many nodes there are by doing 2 to the power of the level, which is 0. So if I do 2 to the power of 0, it's going to equal 1. That is, we have one node. If we go a level down and say, what about level 1? How many levels do we have? Well, we have 2 to the power of 1, which equals 2. All right, let's keep going. What about level 2? How many nodes in total do we have on that level? Well, we have 2 to the power of 2, which is equal to 4. And then one last level, let's say level 3. How many nodes are we going to have in level 3 in a perfectly balanced binary tree? Well, 2 to the power of 3 is going to equal 8. Oh boy. We just did some math here, and I promise that this course isn't going to be that mathy, but bear with me here. I want to explain to you what O log n means. Knowing what we just did now, and knowing that these are the total number of nodes, if we imagine that this data was in an array, that means we have 8 places that we need to iterate through, 8 nodes that we need to check, perhaps to search for something. Well, based on this formula here, that means that we can find out the number of nodes in a tree by doing 2 to the power of h, or the height, that is the level. If we know how many levels our binary tree is, we can find out how many total nodes there are. 2 to the power of h minus 1. Now, why this minus 1? Well, if we go back to our diagram, this binary tree, we have 1, 2, 3, 4, 5, 6, 7. We have 7 total nodes, and the tree is 1, 2, 3. The height of the tree, well, it's 3 levels deep. So 2 to the power of 3 minus 1 is 7 nodes. Now, if we actually simplify this, we can just simply say that the log of nodes is going to equal the height, or the steps. And I use log here. Just in case you're wondering, log simply means that log 100 is equal to 2. Because 10 to the power of 2 equals 100. So all I did was, using this, I simplified and said that log nodes is equal to the height, and we've dropped -1 here because it's insignificant. But log nodes is the number of steps or height. And let's change this to steps that we would use in a tree. Let me show you again in our diagram. Log n simply means that based on the height, the maximum number of decisions, let's say we're looking for a specific node, that we're going to take is going to be log n. That means, is this the node we're looking for? Nope. Then we either go left or right. And let's say we go left and say, is this the node that we're looking for? And that's our second step. If the answer is no, then we either go left or right, and we say, is this the node we're looking for? Yep. So we have maximum 3 steps here, instead of if we went 1, 2, 3, 4, 5, 6, 7 steps. You see that there's some sort of efficiency here. And coming up, we're going to learn about binary search trees, where we're able to minimize those steps instead of visiting every single node. So when you see the notation of O log n, don't get startled. All it's saying is that the choice of the next element on which to perform some sort of action is one of several possibilities, and only one needs to be chosen. We don't have to check both. And a good way to think about log n is when you're looking through a phone book. You don't actually check every single person in a phone book, do you? Instead, you can simply do what's called divide and conquer by looking based on where their names alphabetically begin. You would open up the book to where you think the letter will start with, the name will start with, and then keep dividing and conquering until you get to that person. You only need to explore a subset of each section before you eventually find someone's phone number. So just think of that. O log n is just like looking through a phone book. And the reason that I just talked about O log n in such detail is because it's an important concept. It's really, really fast. As you can see here, O log n is this light green good area. That's even better than O of n, linear time, because we don't need to check every single element. And in the next video, we're going to talk about the most common tree that you're going to see in a lot of places, called binary search tree. And as the name suggests, it allows us to search really efficiently. And just by looking at this graph, you might be able to think about how a place like Google and Google search might find this extremely useful, right? When we search through Google, they have a ton of websites, a ton of nodes to search through. How are they able to give us an answer to our searches so fast? If they used O of n, time complexity, it's going to take a lot of time and it's going to be really expensive for them. So instead, they use a tree structure or a tree data structure so that our searches can be a lot faster with something like O log n. I'll see you in the next video. Bye-bye.